For the people here, you all know Mark, right? So he gave the first very cool visualization lectures. Unfortunately, he's back in Austria. So we're just streaming him live from Austria to give the last lecture on visualization, storytelling, and networks, right?
Yep.
Yes. So I'll just hand over to him. Have fun.
Thanks, Verena. Welcome, everyone. Welcome to CS 109. I'm sorry that I can't be there, but I hope the setup will work out fine today. All right. So it's hard for me to keep eye contact with the camera because I need to look at the slides too, but it should be okay. Yeah, I'm going to talk about graph and network visualization, and for that I need to give you a little bit of background in terms of graph theory. You will probably know most of that stuff from other classes, and then I'm just showing you what people are doing to actually presenting graphs and networks. And the second part, which will be much shorter, is on visual communication and storytelling, and this should just give you a few simple rules that you should try to follow for your final presentations and for your website that you create and for the material that you submit for your project. All right, so graph visualization. As you know, graphs are really omnipresent if you look to any kind of applications. Like if you look at GPS navigation, of course, what is in the background is a huge graph. Then if you look at probably the biggest graph is that Google has indexed, and they're just using that graph to doing their page ranking. Then, of course, Facebook is just a huge graph. You have it with electronics, so if it's about hardware, it's of course important to get a very compact layout on the motherboard of a computer, for instance, or also if you have an underground map, that's just graphs that you have. Yeah, this is another example. It's a poster showing biochemical pathways, and it was published by Roche. So Roche is a large pharmaceutical company, and this is actually a 4 by 2 meters poster that you can put on the wall of your office, and it's showing all chemical reactions in living cells. Yeah? But of course, the bio community moved on to more interactive versions that you can look at on your computer. And this is the last example that I have. It's showing the Facebook network, so who is connected to whom. And the dense regions are, of course, also densely populated regions that are using Facebook. So you see the US and you see Europe here. Can you see my mouse pointer too? I'm not sure. Verena?
I can see the hand there, but it's very small.
Yes, this is the mouse pointer. Okay. Yeah, never mind. So what's interesting here is if we move a little bit further to the right, so what about China? Yeah, China is completely missing because, of course, they have shut down Facebook and they're using their own social network. So this is why we have a black spot here. Yeah, and this is just visible because we have a really nice graph visualization. Okay, if you want to see a full case study, then I can highly recommend the talk by Nikola Christakis, who is also a professor at Yale, and he's talking about how a variety of traits, such obesity or happiness, actually spread through a social network from person to person, which is a really interesting talk, and he's using graph visualization to convey his messages. Okay, now before I show you what we can do in terms of representing a graph, some really basic stuff about graph theory. Let me start with an example. So there's the Königsberg bridge problem. I'm not sure who of you heard of that. It was so it's very early. It came up in 1736, and Leonhard Euler actually he tried to find a solution how to get a tour of the city of Königsberg, which is Kaliningrad in Russia today. And his goal was actually to cross each of the 7 bridges that are in the city just once and being able to see all the parts of the city. So what you have here is 2 islands in the center, and you have the land which is above the river and below the river. And he was the first one who formulated this. He reduced it to a graph theory problem. So what he did was to actually remove all the details about the land. It was just he collapsed, or he removed all the details to just have nodes, these tiny round objects here, and the bridges are connecting the nodes. Yeah? And this way he was actually able to show that it is not possible to visit all parts of the city by just crossing each bridge once. Yeah? And that was one of the first examples of graph theory applied to a problem. So if we try to define a graph, it consists of vertices and edges. Yeah? And edges connect the vertices. Yeah? That's very simple. And vertices are also referred to as nodes, and edges are also referred to as links. Yeah? All right. So we say it's a simple graph if a graph does not have multi-edges. Yeah? So a multi-edge in this tiny sketch representation that we see here, a multi-edge would be 2 nodes that are connected by two edges. Yeah? And if there is a multi-edge, then it's not a simple graph anymore, but it's a general graph. And the same holds for loops. If there is a loop in the network, then it's not a simple graph anymore, but a general graph. Okay, then we have something like a directed graph or a digraph. So this is if we have, if it makes a difference, if A is connected to B or B is connected to A. Yeah, these are 2 different types of edges. Then it's a directed graph. Another important class in computer science are hypergraphs. So hypergraphs is probably a little bit different than what you would think of a graph. This is when you have edges that connect multiple vertices at the same time. So what you see in the sketch here is these areas, these darker blue areas is one hyper edge connecting 4 nodes at the same time. An example would be if you have a social network and you have 4 people that all like, I don't know, some kind of fan page, Harvard Outing Club or so, and if they all like the same page, then the Harvard Outing Club would be the hyper edge connecting them. Yeah. Okay, then there is something like an independent set. So if we remove all edges and we just have the vertices, then it's called an independent set. And this is important if you have a graph which is only about some attribute of the nodes, then you could just get rid of all the edges and look at it as an independent set. Then another interesting class is a clique. So a clique is a fully connected graph. So every node in this graph is connected to every other node. And this is important if you look at graph algorithms that try to identify these highly connected clique subgraphs. Then there is something like a path. Yeah, this is very intuitive. If you have a certain, a path contains only edges that can be traversed. So if we want to go from from this node on the left to the node on the right, then we need to follow the path. And this is what the GPS navigation system is doing. It just tries to find the shortest or the fastest path through the network. Then we have a tree. So trees are very special for visualization because there is much we can do with trees that make them different from graphs. And you will see that in a couple of minutes that trees are really special for visualization. So a tree is a graph that does not that contains no cycles. Yeah. So this is the example that you can see at the bottom. You have a tree. So if you would pick one node and put it just above, then it would form this tree shape. Yeah? And if we would add one edge to this tree, then we would end up with a network, and we would validate this property of a tree, and it would no longer be a tree. And I need to introduce that because you need to be aware of these different graph classes in the rest of the lecture today. Then there is an unconnected graph. So if we have a graph that is composed of multiple subgraphs that are not connected to each other by any edge, then this is called an unconnected graph. A related concept are articulation points. Yeah, articulation points. This is a very important concept because if you would remove this node, which is the articulation point from the network, then the network would be separated in two subgraphs. Yeah, so this would be in a social network. It would be a person that connects two completely different sets of other people. Like if you have a friends network which is related to your college, and you have another friends network which is related to your I don't know, to the kids in the neighborhood where you grew up, then you're the only person that connect these two sets of people, and that would be an articulation point. Then there's something like a biconnected graph. So if you have a graph that does not contain any articulation points, then it's called a biconnected graph. So we could remove any node in this graph without separating it in multiple subgraphs. Yeah? And this would be important if we would plan, I don't know, a fail-safe computer network. Then, of course, we want to have a situation where we could shut down any of the computers without harming the rest of the network. Yeah? Then the last class that I want to tell you about are bipartite graphs. And this is an interesting class because you have two independent sets of vertices that where you only have edges between these two sets. Yeah. So you see a bipartite graph on the lower right here, and you have circles and squares. So you have two different types of nodes, and only circles are connected to squares, and you have no edge between two circles or two squares. An example where you find this is, for instance, in this biochemical network that I had before, where you have chemical compounds and enzymes. And you have chemical compounds that are the input of a chemical reaction, and the enzyme is catalyzing this chemical reaction, and then you have again chemical compounds as an output of this chemical reaction. And this output could be again the input of the next chemical reaction. So you only have compounds connected to enzymes and enzymes connected to compounds, but you don't have a direct connection between them. Yeah? And this is called a bipartite graph. All right. So I could go on and on. There are 1,000 different graph classes. But I guess the most important ones for you are trees, bipartite graphs, networks, and hypergraphs. Yeah? And we will look at different visualization techniques for these main classes that we have. Okay, then in graph theory, you have all kinds of different measures and metrics that you could use for your application that you want to accomplish. So, for instance, there is something, and I only give two examples here. There's something like the node degree. If you look at the node and you count how many edges are connected to this node, then this is called the node degree. And for instance, an application would be if you have a social network and you're looking for highly interconnected people that are opinion leaders, for instance. Then they should have a high node degree, right? Because they're connected to really lots of people, and if they're posting something, it will reach lots of different people. And the second one would be the diameter of a graph. So if you look for something like the longest, shortest path, and this is called the diameter. And these metrics, if you go to any graph library that you also use for graph visualization, for instance, then you will find these as methods that you could just calculate in your graph. Okay, yeah, I have 2 slides about graph algorithms. Of course, there are plenty graph algorithms out there. Probably the most widely used are DFS and BFS. So it's depth first search and breadth first search. And this is used for traversal of graphs. Yeah? On the left-hand side, you see the BFS algorithm. And this is useful if you're looking for neighborhoods. Like we have a focus node, which would be one person, for instance, in a social network. And I'm using this social network example over and over again to just illustrate the concepts. If we're looking at one person and we're trying to find out who is connected to this person, then we would just we follow all edges and try to find the persons that are connected to this. And we do this recursively. So if we are at the persons who are one hop away, we again take all the friends that are connected to this person again. For instance, if LinkedIn suggests you people that are connected to people where you have a direct connection, and they're suggesting you that you could also connect with these other guys. Yeah? And this is done recursively until you have reached the end of this graph. Yeah? And this is called breadth first search. The other one would be depth first search, and here it's the other way around. We again start with one focus node, and then we are not going in all the directions at the same time, but we are going into the depth. So we are just following an arbitrary edge of this node, and we mark it as visited. And then we again follow an arbitrary edge of this next node and do it again and again until we have reached a node that has no further edge. Yeah? Then we go back and we try to follow another one. Yeah? And this would be a classical, it's called wayfinding backtracking strategy. So like Hansel and Gretel, if you try to find the exit of a labyrinth or something, then of course you would not use a BFS algorithm, but you would use DFS. You would just pick a direction and put a breadcrumb on the floor, pick another one, until you have hit a dead end, and then go back and take a different junction. Yeah, it's very intuitive. And the second, yeah, and you do this until you have visited all nodes in the graph. The second graph algorithm that I want to briefly show you is topological ordering. This is also a very important concept that you would, for instance, need for scheduling jobs. If you have a CPU, so a central processing unit, and there you try to find an order. If you just have one CPU, let's say, and you try to find the perfect order how to process the jobs, yeah, then you would need this topological sorting or topological ordering. So what you do is you have this graph. So you know, okay, process A is related to process B because process B needs the input or the result of process A. And you have this kind of relations between the jobs. An example here would be if you try to dress yourself in the morning, yeah, then you have different kinds of relationships or preconditions for the different nodes. Yeah? Of course, you would need to start with the underwear before putting on the pants, and then you can put on your shoes. Yeah? But you can't put on your shoes and then put on your pants afterwards. Or at least it will be hard sometimes. And if you try to bring this into an order, this is called topological ordering. Yeah? So, and this is not unique. Yeah? So we could start with the socks, of course, but we could, of course, also start with putting on the watch, yeah? Because it does not have a relationship to anything else. Yeah? It doesn't matter when I put on my watch. And these are all graph theory problems. So they are really hard to compute graph algorithms, like finding the longest path in a network. It's NP complete. So there's no solution which works in polynomial time. Yeah, it's always exponential. Or finding the largest clique, or finding I don't know, the minimum degree spanning tree, and so on. But I'm not going into details here. But just keep in mind that there are graph things that you want to know about the graph, which are really, really hard to calculate, and you actually can only find it's an optimization problem, and you can't find really a solution in polynomial time. Okay, so this is just all the background that I want to give you about graph theory, and this is, or some of the parts you will know now, you will need to know now for the visualization techniques that I'm going to introduce. So let's set the stage for the rest. So as you know, we have a graph as a data set, could be any kind of related to any kind of domain, doesn't matter. And then we want to create a graphical representation. And the process to do this is called visualization, of course. But of course, it's important to have a certain goal or task in mind, or this is what the user wants to accomplish by looking at the graph or by interacting with the graph. The problem that we have here is we have really a wealth of different representations. We have, as you've seen, lots of different classes of graphs, and we have also different tasks or goals that users want to achieve by working with the visualization. So the main tasks, so what people want to do with graphs, you can generalize it to two different types of tasks. The first one is called attribute-based task, and the second class is called topology-based task. Yeah? So with an attribute-based task, it's about the attributes of nodes or edges. Yeah? Attributes of a node or an edge would be, if you have a social network and one node is a person, then an attribute of this person would be the age. Yeah? And if you have a topology-based task, then this is really about the connections between them and not about the attributes. So I'm not going through all these tasks. So what people usually want to do is they want to localize something, they want to quantify something, or they want to sort or order it. Yeah? And I will just give you an example. What's the difference if you have a localization task? What's the difference between attribute-based tasks and topology-based tasks? So the attribute-based task for localization would be just find me the edges with the maximum edge weight, or find me all the persons in the social network that are below 30 or so. Yeah? And the topology-based task would be find me all people that are connected to a certain person. Yeah? This is about the topology and not about the attributes. All right, so this is what people want to do with graphs. But the question is, how can we enable them to do that? And there are three different types of graph representations. And these are, if you look at any graph representation that you will find, you can always go back to these three classes. The first one would be a node link diagram. Yeah, that's the most intuitive for you, I guess. Because when you think of a graph, you will think of it as a node link diagram. But there are also other representations which are quite interesting. You could use a matrix or also an implicit layout. And I will give you a few examples. Okay, let's start with node link diagrams. So in a node link diagram, we have nodes, which are points or some kind of objects, and we connect them using lines or arcs. Yeah? And we could use different layouts, like we could just arrange it in any kind of shape. we could arrange it, the nodes along a grid, like in this case, or along a circle, like in this case, or it's also an option that you have a graph where you can't move the nodes. And an example would be if you have a map, of course, and the cities are your nodes, then of course you can't move the cities. So the layout is fixed. But if we don't have this restriction, then of course we can move the nodes to any position we want. But finding a good layout for a node link diagram, it's a really hard problem because you have competing goals that contradict each other. Like you want to minimize edge crossings. Of course, if you have lots of crossing edges, people will not be able to see who is connected or which node is connected to which other node. You would have a very you want to have a very compact representation. Another goal could be that you want to have a uniform edge length. There shouldn't be edges which go around corners also. Another goal would be symmetry. You say, I have a tree and I want to look at, I want to make it look similar or to have a symmetry. Let me give you two examples where you see what I mean by conflicting criteria. So on the left-hand side, you see two, so it's the same graph, so it's the same data, but you have different goals. Like the goal in the top left case would be to minimize the number of edge crossings. And the goal is of course accomplished because we have no edge crossing in that case. But if we would go for a uniform edge length, then of course the version at the top is no option because we have a really long edge. If we want to have shorter edges that should be almost of the same length, then we would need to validate this edge crossing criteria. So here we would have a crossing edge. And the same applies to space versus symmetry. Here this is going for symmetry, and this is trying to utilize most of the space to get a nice looking visualization. So this is an optimization problem. There is no perfect layout. If you have a complex graph, then you can always just try to find a good solution or try to create an algorithm that finds a good solution, but it's not possible to just create the perfect layout in most of the cases. In terms of layouts, one of the most widely used is force-directed layouts. You may have seen them. The idea is that you have a physical model working in the background, where the edges can be seen as springs holding together the nodes. And the vertices are repulsive magnets. So nodes, of course, should not overlap, so they repulse each other, but they're connected using springs. And this is a simulation that runs in the background, and the goal is to minimize the overall sum of the forces. And you will see how this works when I open it in the browser. This is a force-directed layout, and you see it's slightly moving all the time. This is because the physics engine or the physics model is running in the background. So if I would just take a node which is only connected to one other node in the network, then it has almost no effect on the rest of the nodes. Because the force along this single edge is not too high. But if I take one node in the center, all the other nodes will follow me because it's a very central node. And this is called a force-directed graph. And it's fun to play with it, I guess. Okay, I'll go back to the presentation. And I hope you can see everything that I show in the browser, but if you don't interrupt me, I assume everything is okay.
Working well.
Yeah, great. Okay, so but what should we do if we have large networks? And we had this example in one of the visualization lectures before, and I called it a giant hairball. It just looks like a hairball where you can hardly see any details. We see there is some cluster on the lower left, but the rest it's just a hairball. And we already talked about this concept of abstraction and aggregation. So how people try to work with these kind of graphs are to find an abstraction that joins multiple nodes to a single node. Yeah? And this forms a hierarchy. Yeah? So if we have 30,000 nodes here on the upper left, then we could, if this is a social network, and all these nodes, they are close together in this force-directed layout, so obviously they have something in common. And let's say all of them are from, all people in this blob here are from Austria or whatever. Then we could say, well, we just show one single node for all the people, summarizing all the people in Austria. Yeah? And this we do. This is what we do for all of the graph. Yeah? And then we could again join all nodes which are representing countries in Europe or countries in the US to form a single node again. Yeah? And this is how you reduce the size of the network. And then you allow people, so then you could just show, this is a different example from biology that is shown here, but it doesn't matter. So you would just show to users this this highly abstract version of the graph, and people can just click on the nodes and get all the other nodes inside them, which will be shown then. And I think I have an example here. It should work in the browser. So as you can see, it's also a force-directed layout. Yeah, so things are following when I drag here. And when I click on the node, they will be merged. Yeah, and this is a hierarchy, so it's a tree. And if I click on this node, all the other nodes will be merged. Yeah, and this helps tremendously to actually tidy up the visualization. And if I would click on the center node, of course, I would just have this tiny node here. Yeah? But this is the basic concept, and it's called aggregation or abstraction. Yeah? It's a very powerful concept to handle large amounts of data. And there's a really nice demo, and I can highly recommend it. It's worth the time to watch it. It's the presentation, or one of the first, or it's actually the first interactive demo that was given at a computer science conference. Or it was the first interactive demo that happened to be at a computer science conference. And it was in 1968, given by Doug Engelbart, and he actually showed this tree representation which was interactive, which was amazing for that time. So he was able to, for instance, click on produce, and then it collapses all the sub-items here. Yeah? And what he had in the background was, of course, this abstraction hierarchy, like what you have in your file browser, a tree. And it's called now the mother of all demos, because it contained really groundbreaking concepts, because it was the first demo showing the usage of a mouse. It was the first demo showing the usage of video conferencing. It was the first demo showing this abstraction and interactive navigation on a computer, and so on. It's really amazing at that time what system they built. Okay, let's move on to if we have a network, we can always decide to show it in a radial layout. A radial layout is when we arrange the nodes in a concentric way. And this would be a tree again. So we have some kind of root, which would be the root folder on your hard disk, for instance, and then you have the subfolders and the sub-subfolders and so on. And this is called a radial layout. And this was the example that I was showing in one of the previous lectures. It's called MISB, where it's work by a PhD student who used to work in the group of Hans-Peter Pfister, who is giving the visualization course at Harvard. And this representation is actually comparing two genomes. and people can select a reference chromosome, and you see them all the connections to the other chromosomes. But I'm not explaining it again in detail. But you will see it is this concentric layout that makes it possible to show these connections across this free or empty center space. Okay, if we have a lot of nodes, then we somehow need to deal with edge clutter. Yeah, edge clutter is if we add, so if we have this radial layout and we add many nodes, many edges. Yeah, and this is just if we have 100 nodes and we only show 6.3% of all possible edges. Yeah, it's almost black already. Yeah, so. But there are really cool ways to actually fix this. And one approach is edge bundling. And I already discussed edge bundling in the context of map visualization, where you have lots of edges crossing a map. You see the US and flight connections between different cities. And then these are bundled, and then you see these main streams connecting the different edges, connecting the different cities in that case. If we apply that to this radial layout, then this would be the version where we just show the straight edges. And this is a caller graph. So we have some kind of software library which has a package structure, and packages have sub-packages, and there you have the classes in the sub-packages. So you have a hierarchy on the outside. And if a class calls another class, then you have an edge between them. This is the data that we have here. If we bundle it, it gets much clearer, because you can see, okay, these classes in that packages are spreading out to all these other packages here, and we have 3 main streams that are connected here, which is much easier to interpret. How this is done is it's quite simple to explain, actually. So you project this hierarchy to the inside. So the root node would be in the center, and then we just take this hierarchical structure. And what is done then is you follow these paths along this structure, and you draw these splines. It's just curved lines. So you have 2 nodes which are connected to each other. If you follow the full path and you draw a line instead of straight lines, then you will end up with this bundled version. And this is called hierarchical edge bundling. It was proposed in 2006. And the cool thing is that you also have a factor where you can change the strength of the bundling. So here we have this factor is 0. There we have no bundling at all, and here we have one which has a really strong bundling. And I can show it in the browser. So this is again an interactive version of this software package structure. And if I change this tension here, then you will see this would be without any bundling. This would introduce some bundling, and here I just can increase the bundling, and then it's much easier for me to see where the main connections, where the main bundles are connected. Okay, let's move on to the second type, which is not that obvious. So as I said, node link diagrams are really intuitive. But you could also use a matrix representation to encode the same information, to encode the same data. And instead of using this node link diagram, we use an adjacency matrix. So you have all the nodes here as columns and all the nodes as rows. And if you have a connection between them, you just color this cell. So we have a connection from A to B, and we also have a connection from B to A because it's actually a bidirectional link. It has no direction. And this is called an adjacency matrix. And it's really useful if you're looking for patterns in your graph. For instance, this star shape, it's nothing else if you look at the matrix representation than one fully filled column in this graph. And then you would also have like other patterns. If you're looking for a bipartite graph, then it would be this solid block here. If you look at the clique, then it would be this shape. And if we look at another example where we have a direct comparison between the matrix representation of the graph and the node link version of the graph, there you can see that, for instance, these clusters that we have here would also form a cluster in the matrix representation. So there are certain tasks that work really well in the matrix representation, like when you look for all neighbors of a certain node. You would just go to this, if you're interested in node B, then you would just go to the line of node B and say, okay, A, C, and D are connected. This would be much harder if we have a huge node link diagram, because we need to follow all the edges. But it's not really suited for any kind of task that is path related. If you're, for instance, a path in a node link diagram, it's very intuitive. You say from A to E, from E to C, from C to B. This does not work in the matrix representation because the colored nodes will be not connected in the matrix. So this task will simply not work. So it always depends on the goal that the user needs to accomplish, and then you can pick the right representation. Okay, the third type of graph is called implicit representation. And the idea here is that that edges are not shown as explicit connections, but edges are just encoded using a meaningful positioning of the nodes. I will only explain this example here at the bottom. For instance, this is called a permutation diagram. And this does not scale to large graphs, of course. But the idea here is this would be the node link diagram at the lower left. And you will see A is connected to E. And the idea in the permutation diagram is that you show all the nodes here at the top and at the bottom. And then if you have A is connected to A, you just connect the same nodes with, so B is connected to B, A is connected to A, C to C. And then you read it like this. If you have a crossing, so if you want to find all connections from A, then you just go along this line and try to find the crossing lines. So A is crossing E and D, and that means it has a connection to E and D. And this is actually a really crazy way to encode a graph. So C would be connected to D, E, and C, and B. So here you don't have edges as lines, but you just have them as positioning of nodes. And this will get more clear if I show you these examples. So you could say two nodes share an edge if they overlap, or two nodes share an edge if one node is drawn inside another node, or if they are shown, if they touch each other, then they share an edge. That's meant by encoding edges just using the position. And you will see in a second how this is applied to really interesting data sets. So if we take a simple tree, you have a root node, which is A. That could be a root node on your hard disk, and then you have 4 folders, B, C, D, and E, which are the child nodes. And in an implicit tree, we are just working with the positioning of the nodes. We say A is the root node, and all the other nodes are drawn inside A, and this now encodes that there is a parent-child relation. And this is called a tree map. So this is from the original paper from 1991. Here you see the explicit drawing of a tree, like what you see in a file browser. And this is the implicit version. So the root node would be the full area, and then you start to subdivide these areas recursively. Yeah? And I will give you an example, and then it will be pretty clear, I guess, how this works. So this is a really cool application that you can check out online. It's called the map of the market, and it summarizes to you the whole what happened during the day on the stock market. Yeah, and the hierarchy is the different types of industry, like financial, oil and gas, utilities, telecommunication, technology, and so on. And then in this technology block, you have all the different technology companies. Yeah? And the size of these blocks are the size of the companies. Yeah? So you have Microsoft is, of course, huge, Google is huge, Facebook, Apple. Yeah? And the color is if the stock price went up or down. Yeah? You see a big loser today was Qualcomm. Yeah? They published some, they had some news reports that they have problems in China and also Europe, and then the price went down. Yeah? And we could also say, well, we want to see it for the last 52 weeks. Yeah? And it summarizes us a huge pile of data in just one image. And we would see actually a stock market did well over the last 52 weeks. The biggest winners would be Facebook, Apple, went up 50%, and here are some of the losers, yeah, which are red. So this is very nice, I guess. And the cool thing about that is that it scales to also lots of different nodes. So what you see here is an example, and this is just an example from a publication. They try to encode millions, so 1 million items. Yeah, and for instance, this could be used if you have a network, if you have a computer network. Then if you have a problem in some part of the network, it would turn red. Yeah, and then you can try to zoom into this part. Okay, then there's also, going back to this radial layouts that I've explained before, if you're working with adjacency, you say if they touch each other, if these rings touch each other, then they share an edge. Yeah, so you have the hierarchy encoded here, and this is showing the caller graph. So this is showing a website, and you have different entry points on the website, like this is the home page, and then people are clicking on a certain product, and then on another subcategory of products, and so on. Yeah? And you see, this is the portion how many people entered the website onto the home page. Yeah? And this, again, summarizes a huge hierarchy that you have in the background. And there is a really nice collection of, if you have a tree and you want to visualize it, there is a collection called TreeVisNet. And when I go to this website, it just opens up any tree visualization that was published over the last 30 years, I would say. And you could just say, okay, I'm only interested in explicit, so node link diagrams, and I'm only interested in 2D versions, and so on. Yeah? So this is a nice resource if you try to find a way to visualize your tree. Okay, yeah. To sum these graph visualizations up, is you have node link diagrams, we have adjacency matrices, which I've explained before, and implicit versions. And the only restriction is that implicit versions, like this tree map, of course, can only encode hierarchies and no full graphs or networks. Yeah? So when you pick one, you need to think about this restriction. Okay, and of course you can also combine them. So you could create a hybrid version between a matrix and some, so like between a matrix and an explicit version. Yeah? Okay, yeah, now before I switch to the second topic, visual storytelling, I want to briefly talk about hypergraphs. Yeah? Hypergraphs are interesting because, as I said, you have hyperedges that connect multiple nodes at the same time. And for instance, let's say we have a scatter plot, yeah, and the dots in these scatter plots are different countries. Yeah? And if we want to somehow say all the green dots, they are countries in the US or states in the US, then we would try to create this region around, which is the hyperedge. Yeah? And this is called the subset standard. And there's also another version. So you have, for instance, this edge here is connecting 3 nodes, and then at some point you need to split this edge, and this is called edge standard. And this is, for instance, used in this biochemical network that I've shown before. And now, before I move to the second topic, one side note, which I think is really important because people are using it a lot, and it has certain limitations. It's about Euler and Venn diagrams. Yeah? And I'm sure you have seen a lot of them. Yeah? But it's actually not so widely known what's the difference between them. So a Venn diagram actually, so you have these intersecting sets. Yeah? And it's about the intersections between 2 different sets. If we have an Euler diagram, it only has the intersections that actually exist. Yeah? Like if we have 2 sets, which are vertebrate animals and invertebrate animals. Yeah? And actually there is no intersection between them, yeah? Because an animal can only be vertebrate or not vertebrate. And if you show it as a Venn diagram, then you would actually have intersections that do not exist. And yeah, of course, this does not scale to multiple different sets. Yeah? And there are scientific publications where you see this kind of really horrible creations. Yeah? This is showing 4 different sets, and you have all different intersections. Yeah? And here some of the intersections are missing. So that is actually not a real Venn diagram. But here you have all different combinations, so this would be a real Venn diagram. And on the right-hand side, you just see a meta joke. If someone asks you what the difference, or what the difference between a Venn and the Euler diagram is, then you would actually be in this 3rd section here. So it's people who know what a Venn diagram is, people who know what an Euler diagram is, and actually these are just the people who know the difference between them. Yeah. Okay. Yeah, and yeah, just to summarize the first part, what open source tools are out there. If you have a huge graph and you want to visualize it, you could use Gephi, which is a Java-based open platform for visualizing graphs, and it supports all kinds of layouts and graph algorithms and so on. It's really nice. Another widely used tool is Cytoscape. It's also open source. You can use it, you can load your data, you can visualize it using any kind of technique that is out there. There's also a web version, which is JavaScript based. Yeah, it's also really nice. And if you have some graphs to visualize, then please try it out. And this is just for sake of completeness. There's also a Python library. It's called Network X, and it's an interactive Python visualization that works in your browser. Okay. Now to the second part, which will be much shorter. So I will probably need 20 minutes or 15 to 20 minutes to finish that part. So you might say, well, visual communication and storytellings, they're soft topics. And of course you're right, but they're very, very important. And they're also important for your projects. At least that's what Verena and Raphael told me. So these are some simple rules that you can follow to make a better presentation, to make a better IPython notebook that tells a story actually, or to create a better website that you also need to deliver. So let me start by probably the most prominent way to present something is to use a visual tool like PowerPoint or Keynote, as I use it now. But they have the same limitations, and people use them in really horrible ways. Yeah, when you just Google death by PowerPoint or bad PowerPoint slides, you will see really amazing examples of what can go wrong. Yeah, and I just want to focus on this last example here, which is interesting because it was a slide that has a tremendous impact. Yeah, and this slide was actually used at the press conference of the when they presented the discovery of the Higgs boson. Yeah, and as you know, they built this large hadron collider, and of course, this is an incredible piece of hardware, yeah, which is amazing, yeah, and they put billions of dollars in the system to actually build it. But then they had this press conference, and I mean, it was an amazing finding, and they presented it really poorly, yeah. They had this slide, which is not only ugly, yeah, that's not the main problem here, but it is really for the wrong audience. It's created for the wrong audience. So it was a room full of press people, and the whole world was watching, and they had this slide with lots of detail that you can't understand at all. Yeah, and this is a really good example of poor communication. Yeah. So this should not happen to you. And related to this is the bad image of the scientist. And I took these slides of the presentation that Hans-Peter Pfister gave last year in the data science course. So I'm just repeating what he told last year to students for their final projects. Yeah? And the image of the scientists, it's quite bad, to be honest. Yeah? So so what do these guys have in common? Yeah? And I know this is not really interactive today, so I'm answering my own question, which is kind of weird. They all have in common they're white males, or at least yellow, yeah, this Professor Frink from The Simpsons. But they also have in common that they're somehow crazy, yeah. And this is the picture of scientists in the general public, yeah. Like, you know, this picture of Albert Einstein, yeah, or Getafix, which is called Miraculix in Europe, which I find interesting that there is a different name in Europe for Getafix, or for this guy who is creating this superpower drink. Anyway, the message here is that the image of scientists is really bad, and that's probably also their own fault, because some of the scientists are bad in communicating their results. So you should do better, and there are some simple rules, and I'm not going to talk about how to visually design your slides. Yeah? So this is not the task in the remaining 10 minutes. But I'm actually so Hans-Peter created a couple of rules that you can follow. So what are the reasons to communicate? And you should actually try to convey what you have learned in your project. So don't tell the audience what you did. Tell the audience the most important things they should know, but probably do not. Yeah? And the second reason to communicate is to get feedback from others. Yeah? And this is also relevant for your professional life. I think you will hear many different presentations. Yeah? You will sit through meetings with tons of presentations, and when you do a presentation in these smaller groups or so, then really try to do a good job, because it's the best way to get feedback. Yeah, and you will probably, or I hope so, you will be surrounded by smart people. So it's well spent time if you put effort in the presentation, because you will get really valuable feedback. Yeah, yeah, and there are these. From journalism, there are these 5 W's, yeah, and actually more or less, because in journalism they're a little bit different. They have when and where. So a story should contain when something happened and where something happened. But this is not so important for visual communication. So the W's here are, you need to know who is your audience, yeah, and it could be different audience for different talks or different presentations. What is the motivation behind your projects? What questions are you answering? What is the context of your project? So is there some related work? Of course there will be, you might be inspired by something, and it will not be something which happened completely separate from the rest of the world. And the last one would be, why should I, or why should the audience care? So what are your major interests? Is there something surprising? What would be the impact of the work? So let me start with the first one. You need to know your audience. Yeah? And I know that you're, who is sitting on the other end at Cambridge today. But if you would have these two crowds of people, yeah, then you would probably give a different presentation. Yeah? And this is also true for your projects, because you need to create you need to create a website, for instance, which is for a broader audience. It should be readable for the general public. It will be publicly available on the web, and non-experts will be reading it. Yeah? So you don't need to put in all the details. You just should describe it on a higher level. Yeah? And the second audience for you are the experts, the instructors. So Verena, Raphael, and all the teaching fellows. Yeah? And for them, of course, you need to provide all the details, all the insights. And these details should go in your IPython notebooks. Yeah? So you also have different audiences. Yeah? And you need to put yourself in your audience's shoes. Yeah? And that's not that simple sometimes. Okay, so the next advice would be that the audience is lazy. Yeah, I'm not saying that Verena and Raphael are lazy, and but in general, if you have an audience, they don't want to think too much. Yeah, if you're not telling them what you know, and if you're not presenting it in the right fashion, they will not have time to think about the context of your project, about implications, about potential problems. They would need to think, and they would need to try to understand your slides. And it shouldn't be like this. So the audience should not invest too much mental effort to actually understand what you're saying. And there are presentations where people just try to present something in a very complicated fashion to show that they're smart. Yeah? But this is, of course, a really poor way of communication. So you should really aim for, your goal should be that the audience is understanding everything what you're telling them. Okay, then it's also about framing. If you write your websites and your IPython notebook descriptions and so on, then tell the audience, here is the way to think about the problem. And that was the question I was trying to solve. And if it's done well, also your solution might seem obvious, yeah? But that's a good thing, yeah? And that's what you try to accomplish. Yeah, and you could also, for instance, put some cool results at the beginning. In journalism, this is called a lead. Yeah, you could put a lead at the beginning of your website. Just in the second sentence, tell them what you have found. Yeah, if you have a cool result. Yeah, I added this slide because I find it really funny that you see it in so many different scientific presentations. Yeah, there's a slide which is just telling, this is my outline, and then the speaker says, okay, now first I will introduce my work, then I will tell you what others have done, then I'm going to present my methods, and I'm going to tell you how I implemented it, and finally I will conclude and tell you about future work. Yeah? And my former PhD supervisor, he actually takes a picture every time he sees such a slide, and he has a huge collection of all kinds of different variations of this outline slide which says nothing. Yeah? And if you have if you're in the situation of having such a slide in your presentation, then just get rid of it, because it doesn't tell nothing. It doesn't tell anything. All right. So yeah, and you could try to tell them something they didn't expect. Yeah. For instance, if you're giving a talk about bacteria, then you could say, well, have you heard about this 5 seconds rule? Yeah, and this 5 seconds rule is when you drop some food on the floor, if you pick it up in 5 seconds, then it's not significantly contaminated by bacteria. Yeah, and you could then ask the audience, or you could tell them, well, there are lots of people who believe that, but this is not true. And then you try to explain them why this is not true. And there's also a great comic about that, which I really like, so that bacteria are waiting these 5 seconds until they will get to your food. Okay, then this is called the curse of knowledge. If you know something, it's always very, very hard to communicate it to someone who doesn't know it. Yeah, because you can't imagine that you don't understand it, and when you try to explain it, it's not that easy. Yeah, and the rule here is try to be as concrete as possible. Yeah. All right, this is just an example from New York Times, where they had this 100-meter sprint, and they compared how we got faster over the last, I don't know, 100 years or so, and then compared the different results of the Olympic Games of the 100-meter sprint. And this is you can watch the video online, and I'm not showing the video now, but this is a really good example how to tell an audience a story. Okay, and yeah, 2 slides before I'm giving a brief introduction about visual storytelling is you should end your talk with a positive note. Yeah, say the future is bright and my work has obviously lots of impact. Yeah, but what you hear in many cases is that someone will end the talk with problems and minor issues with the implementation or so. But this shouldn't be the case. Yeah. So have a really catchy end and say, well, I did a great piece of work, because that will stick to the audience. And the last advice is less is more. So keep it simple, and keep it simple, stupid, is the rule. And if you write your website or your IPython notebook description, really go through the text and think about every word, every sentence, and every sentence and word should matter. If it does not matter, throw it away. Yeah, you really should have a piece of text that is very condensed and very precise. And the best example would be this Nature paper by Watson and Crick. Yeah, and they presented the double helix. Yeah, and they got the Nobel Prize. So if you present it in a really concise way, and this was a one-pager, yeah, then you're up for the Nobel Prize. Okay, and you should try to follow these rules that I've presented. So there are lots of different examples of representations that are not effective, but you should really try to be better and try to create very clear and crisp graphics. But of course, they are not. They shouldn't be. So we're not looking on any detail that we presented in this visual design respect. Okay, so I have 5 slides or so. Then I'm at the end. It's about visual storytelling and the art of telling a story. So in your IPython notebook, what you should try to do is you should try to tell a story. And the New York Times is probably the best newspaper that can do that in an interactive fashion. When you go to their website, you will find a great collection of storytelling examples. Yeah, you will find it to the elections this week. You will find it to all other kinds of sports topics, explaining the spin in baseball that you have with a curveball and so on. Yeah? And there was a paper on storytelling written by Jeff Hare, who used to be a professor at Stanford and then moved to University of Washington. And they looked at 58 case studies, 70% from journalism, 20% from business, and 10% from research. How people presented stories, so findings. And they actually found out that you have 3 different parts. It's about the visual design, so you need to show plots or visualizations. It's about the messaging, so you will have some text which should be very clear, as I said. And sometimes you have some interactivity. And this, of course, does not apply to your project because it's not about interaction. Yeah, and you have different ways, like you could present it in a magazine style, you could present it in a slideshow, you could present it in a movie, and this is also what you need to do for your projects. You need to create this 2-minute narrated screencasts, and there you also need to think about the stories. And you will see it's not so easy to first tell the user what the question is, then tell them how you have what the problem is and what the challenges are, how you have done it, and what the results are. And try to create a nice story that will encourage the user to read on. Okay, so these are my last slides that I have. It's examples from the New York Times where they really did an amazing job to tell stories based on complicated and large data sets. For instance, if you go, and this is from October 27, and it shows the cases of the Ebola outbreak, and you will see the bigger the circle here is, the more cases they had in this region, and this is also interactive, so you can move back in time and look at the different points in time. And they will have a whole collection that is trying to take you by the hand and follow a story, which is the Ebola outbreak in that case. So this is just one tiny part of it. And you will find the same for the midterm elections. If I go to New York Times, oh, they actually shut it down like 1 hour ago or so, because now they have this sheet over this machine, and when I made the screenshot today in the morning, they had this graphic here, and then they had all the nice visualizations showing the different predictions of the different states and so on. Anyway, these are just further readings. So How to Make It Stick. It's a really nice book, or this book by Edward Tufte, which I mentioned before. And there's also The Functional Art by Alberto Cairo, or The Presentation. But I haven't read this on my own, but I can just recommend The Functional Art, which is a really nice piece of work. Okay, that's it for today. Are there any questions? Verena, are you still here? Are people sleeping? Then please wake them up.
We're still here and all awake. First of all, I would like to thank Mark for pulling this off. I know it's hard to stay that engaging when you actually can't see your audience. Do you have any questions?
Okay. Then thanks for listening, and have a great time. And I hope to see you again at some point. Bye.